Welcome to Engineers Mindset. Now in this class, I'm going to show us how to employ the Macaulay method to carry out beam deflection. Okay. Now let's say we have a beam. And of course we have the reaction of this beam. Let's call here point A. Let this beam carry a load here. Call this W1. Call this load W2. Okay, let's call the reaction here. Okay, simply let's call here point B, point C, and point D. So let the reaction here be simply RD. Let's say their distance apart are 2 meters each, 2 meters and 2 meters. Okay, let's reaction here be simply RA. First of all, what is beam deflection? Whenever a beam is loaded, it is normal deflection is possible. It must always occur. And deflection simply means the change in dimension of a given beam due to load that is being applied on the beam. That is what deflection is. So whenever a load is applied to a beam, there is going to be an alteration in the dimension of that load, or in the dimension of the beam, sorry. There is going to be an alteration in the dimension of the beam. That alteration gives rise to what is called deflection. That's what we call deflection. Okay. Now, to employ Macaulay's method, this is one of the best and easiest method to apply to solve questions on beam deflection. As you all know, we have three methods of analyzing beam deflection. The first method is what is called the double integration method. The second method is called the moment area method, and then the final method, which is the very best method to employ, is called the Macaulay's method, which I'm going to show us in today's class. Okay, so let's consider now the beam. We have this beam having reactions here at A, having loads W1 and W2 at points B and point C, and then having reaction at point D. So to carry out the Macaulay's method, the first thing to do is to consider a section. So you consider a section XX, consider a section, okay, a section XX at a distance X. Okay, so you're simply saying let the distance be X meters from A. Now you consider this section XX at a distance of X from A. Now when sectioning, you section in such a way that the entire load on top of the beam is included in the section. Whenever you're sectioning, ensure that you section in such a way that the entire load on top of the beam is included. So you do that till the final point load you have on top of the beam, not under. Please take note, you section in such a way that the final point load you have on top of the beam is included in the section. That is where you end your section. Okay, so not the load under, the load on top, the very final load on top, you end your section after the load. All right, so let's do that and see. We said take a section XX at a distance of X from A. And I said if you're sectioning, section in such a way that the entire load on top of the beam is involved in the section. So the final load we have there is W2. I want to section from point A, so I will section somewhere here. So I'm simply saying from here to here, that's the section XX, and you section such that the entire load on the beam. So this is the final load on top of the beam. So after this load is where my section is. So that means I cannot section above point D. This load here or this reaction here cannot be involved in the section. It must be the last load on top of the beam. But if we have any other load, take note please, if we have a load on top here, let's say we have a point load at point D, then there is no point. The load must always be the very last load before the last point on the beam. That's where you section about the last load before the last point on the beam. So if we had a load here at this point D pointing downwards here, then there is no point taking section there. You just end your section here. The very last load before the last point on the beam, that's what we consider our section. Now we simply said let distance from point A to the point of section be simply X meters. So you're simply saying distance from point A to this point is simply X meters. That's what Macaulay's method is saying. In Macaulay's method, we have to employ this now to form just one equation. We employ this to form just one equation, and then we carry out our bending equation to analyze for deflection and slope. Okay, so if distance from point A to the point of section is X meters, what then is the distance of this load? Of course, I have W1. Of course, I have W1. I also have what? W2. So what then now is the distance of W1 to the point of section? What then also is the distance of W2 to the point of section? Simply, what is the distance from this point B to the point of section? And also, what is distance from point C to the point of section? This is what I have to now look for, because I now know distance from point A to the point of section. What then is the distance of this load W1 to the point of section? So if you have been following my series on shuffles and bending moments, we have been doing lots of this on shuffles and bending moments. But just to be clear, I said if from point A to this point of section is x meters, then distance from point B, now I am at point B, which means I no longer need the distance behind. I want to find distance from point B to the point of section. So therefore, I no longer need the distance behind. And distance behind is 2 meters. So I will simply what? Take away 2 meters from where? This x. That gives me distance from the point load here, from W1 or from point B to the point of section. Therefore, distance of this load about the point of section simply becomes x minus 2. Okay, that gives me a distance. Simply remove this distance you don't need. Since I am at point B, I'm no longer at point A, so I don't need distance from point A to point B. I just need from point B to the point of section. Simply take away the distance behind. That simply becomes x minus 2. Okay, so that gives me distance from where? Point B to the point of section. That's the first thing you establish. Next thing you establish now is at the load of W2, that's at point C. What now is the distance of this load from point C to the point of section? It's still the same thing. If from point A to the point of section is x meters, what is now distance from point C to the point of section? Same thing. Now I am at point C, which means I don't need the distances behind. And distances behind include 2 meters and 2 meters. That's simply 2 plus 2, which is 4. I'm moving from point C to the point of section, so I don't need these 4 meters behind. All I need to do is simply what? Take off these 4 meters from where? X. That gives me the distance from point C to the point of section. So the distance of this load W2 to the point of section is simply x minus 4. That gives me distance from point C to the point of section. So that's the first thing to do. After taking the section from point A to the point of section, you call the distance x. Find out what is now the distance of all the forces or the loads on the beam about the point of section. After getting that, we can now employ Macaulay's method. And Macaulay's method is simply what? Obtain moment about the point of section using the what? A very single equation. Obtain moment for a single equation about the point of section. Moment of all the loads on the beam about the point of section. Okay, so let's do that now. So about the point of section, now the point of section is simply xx. Therefore, the moment becomes moment about xx. And this is now equal to, so we take moment from beginning to the point of all the load from beginning to the point of section. So the first load we have here is simply RA, which is the reaction at point A. The moment of this force about the point of section, moment naturally is simply force times distance. The distance it takes this force, of course, this force is really at point A. Distance of from point A to the point of section, we call that what? X. So the distance it takes this force RA to get to the point of section is simply what? X meters. So therefore, the moment of this force RA about that point becomes force times distance. So that means we simply have RA, which is the force at that point, multiplying by the distance x, because from point A to the point of section is simply what? X meters. So the moment of this force is simply RA times x. Now take note, when carrying out moments, you consider downward force to be what? Have a negative moment, while upward force should have a positive moment. So that is why I have RA here times x. So it's positive because it's pointing upwards. This reaction is pointing upwards, so it will give us a positive moment. Now, after the first reaction, the loads on top of the beam now involves what is called the Macaulay's bracket. So before carrying out the moment of this load, you have to now introduce the Macaulay's bracket. And what is the Macaulay's bracket? It's simple, just a bar to introduce what? To separate each of the moments from where? The point of section. All right. So after this RA times x, which is the moment of this force about the point of section, I will now introduce a bar. This bar is called Macaulay's bracket. Now I want to take the next moment about the point of section, and the next moment is moment of this force W1 pointing downwards. Since this force is pointing downwards, it will have a negative moment, so called minus W, and this is a force. Moment is force times distance. The distance it takes this force to get to the point of section is simply what? X minus 2, not forgetting that. So that means I have W times X minus 2. This simply gives me the moment of this force about, sorry, this is W1, okay? So that gives me the moment of this force W1 about the point of section. After that, since I still have another load on the beam, still the same thing, introduce the Macaulay's bracket, simply a bar. So observe that each of these moments are going in with their sign. So the sign is not outside before a bar, no. The sign is inside of the Macaulay's bracket. So after this, I want to take the moment of this other force W2 about the point of section. Still the same law. Since this force is pointing downwards, it will have a negative moment. So minus W2. Okay, so I have this times distance it takes this W2 to get to the point of section. We've already established that as what? X minus 4 here. So that simply becomes X minus 4. This single equation represents what? The moment equation by what? Macaulay's method. So this gives us a moment. So Macaulay's method simply says introduce what? A Macaulay's bracket. That bracket separates what? The moment, each of the moments from one another. That's what the bracket does. So if I observe this bracket now, I know that I have this moment of RE above point of section, which is simply RE times X. The next bracket is talking about moment of this load. The next bracket is talking about moment of this other load, W2, about the point of section. So we obtain these moments. Now, recall from your bending equation, okay, from bending equation, you have that flexural rigidity, which is EI d squared y all over the x squared is equal to what? Moment. That's your bending equation. EI d squared y over the x squared is equal to moment. So that simply means we are going to now employ that. It means moment about xx is simply also what? EI d squared y dx squared. So this becomes the moment equation. So we are going to employ in place of the moment equation. Remember, mxx for Macaulay is simply what? This. So which means I can replace this as what? In place of moment about section xx, I can now rewrite this equation into it. That simply now implies that, okay, I will now have EI d squared y over the x squared. We said that's equal to moment about xx, and moment about xx, we've obtained that from Macaulay's theorem as simply what? This. So the whole of this equation is simply equal to this. So let's bring this down. We have RAX, okay, Macaulay's bracket minus W1 into x minus 2, Macaulay's bracket minus W2 into x minus 4. We simply have this. Now, if I integrate this function, you remember that integration is simply opposite of differentiation. So if I have the squared y over the x squared, it means if I integrate it, I'm going to now have what? It will now step down to what? Dy dx. That's first order because I've taken a reverse direction of what? That derivative. So integration of the squared y over the x squared will simply give me dy dx. So I will simply what? Integrate both sides of the equation. And if I integrate that, I will have dy dx. Dy dx is called the slope. Okay, dy dx is called the slope. Now let's try it and see. Integrating, we have, okay, we have, okay, ei. If I integrate the squared y over the x squared, I will simply have dy all over the x, and this is now equal to, so I'm integrating with respect to x, not forgetting. So that means I will have that to be simply Ra, meaning reaction at A. If I integrate x, this will simply give me x squared all over 2. If I integrate x, I will have x squared all over 2. Now take note, since this is not a definite, okay, so since this is not a definite integral, that is to say, since this integral does not contain limits, okay, so that means I'm going to introduce what? A constant. It's an indefinite integral. So I'm going to introduce a constant. Okay. Now, if you're introducing the constant, you don't put the constant after the Macaulay's bracket, sorry. You don't put the constant after the Macaulay's bracket. You put all the constants before the Macaulay's bracket. So if I integrate this now, I'll simply have RA integrating x simply gives me x squared all over 2. Now I have a Macaulay bracket left. So that means before this Macaulay bracket, I will now put in my constant of integration. So for the first integration, that constant is simply what? Plus C1. Where C1 is the initial constant of integration. Then I will put down my Macaulay's bracket. Now, to integrate the function or the expression in the Macaulay's bracket, we simply integrate x minus 2 as well we have a single variable. Like I've done here, integrating x, I have x squared all over 2. It's still the same thing that I'm going to employ integrating x minus 2 all over 2. Sorry, it's still the same procedure I will employ to what? Integrate x minus 2. I will see x minus 2 as what? A single function. So there is no need to break it down and say integrating x first and then integrating 2. No. Consider x minus 2 as a single function and integrate. So if I see it as a single function, it means the integral of this value becomes, first of all, I have minus w1. So if I integrate x minus 2 now, I will simply have x minus 2 all squared all over 2. Just the same way I will integrate a single function. Okay, so put down my Macaulay's bracket. Okay, same thing applies here. Integrating this now, simply have minus w2, okay, into x minus 4. Integrate this also as a single function. It becomes x minus 4 all squared all over 2. That is according to Macaulay. So if you're integrating what is in the Macaulay's bracket, you integrate it as a single function. The same way you're going to integrate what? A single variable function. That's how you integrate what? All the brackets in the Macaulay's bracket. Okay. Now, this is called the slope equation. Of course, we have a constant there, so we can always look for a way to find the constant. But then again, we need still to what? Integrate again to obtain the deflection equation. So if we integrate again, we are going to have integrating again. Okay, if we simply integrate again, that's now we want to integrate dy dx. If we integrate dy dx, we are simply going to obtain y. Okay, so if we integrate dy dx, we are simply going to obtain y. And y actually stands for what? The deflection equation. Okay, so integrating again, we have e I dy dx automatically becomes what? Y. Okay, because integral of what? Dy dx, integral is simply opposite of differentiation. So the opposite of dy dx simply gives us what? Y. And this is now equal to, same thing here, I will now what? Integrate again this function x squared with respect to x. So this is simply Ra times, now remember, if I integrate x squared, I will simply have x3 all over 3. So that will simply give me x cubed, x3 all over 3. But remember, we have 2 there already, so times that 2 we have done. So if I integrate x squared, I will simply have x cubed all over 3 times the 2 I already have under there. So that gives me that. Plus, if you integrate a constant, of course, C1 here is a constant. If I integrate a constant, I will only have what? The integral variable attached to the constant. So if I'm integrating with respect to x, it simply means I'm going to have C1x. So just like saying integrating 2, 2 gives me what? 2x. So when you integrate a constant, you have the integral variable attached to the constant. So if I integrate C1 here, I will simply have C1 times x, because x is integral variable. Okay, plus of course I will have a second constant C2, the constant of the second integration. So I've always said the constant should always be kept outside of the Macaulay's bracket. Okay, not after the Macaulay's bracket. All right, so I can now bring down my Macaulay's bracket. Now I have here minus w. Okay, let's just put this all over 2 here. So if I integrate x minus 2 all squared, same thing, I will still integrate it as what? A single variable. There is no point expanding this bracket according to Macaulay. Integrate that as a single variable function. Okay, so x minus 2 squared becomes x minus 2 to the power of 3 all over 3 if I integrate it. All right, so I will simply have x minus 2 to the power of 3 all over 3. That gives me what? The integral of that function. Okay, I put down my Macaulay's bracket. Here I have minus w2, okay, all over, put down these 2 here. Same thing now, if I integrate x minus 4 squared, I will still have x minus 4 all cube all over 3. So I have this, okay? Okay, so if I write this equation now, I will simply have EIY, okay, simply equal to, of course, 3 times 2 here gives me 6. So I'll simply have RAX all over 6, okay? All right, so plus C1X plus C2 Macaulay's bracket. So I have the first function here. So minus W1 over 2. Okay, this is W1, this is W2. So minus W1 over 2 here now. 2 times 3 also gives me 6. So this becomes minus W1 into X minus 2 all to the power of 3 all over 6. And finally, I have minus W2 all over 6 into X minus 4 all over 3. So I simply have this. Now, to find the constants of integration, I will have to consider what? Taking boundary conditions. Okay, so we consider taking boundary conditions. Now, what are the boundary conditions? Start with what? The very beginning of the beam. Consider, because remember we took a section and we said, let the distance of the section run from point A down to somewhere around here, which we called XX. I will say distance from point A to that point is simply what? X meters, okay? We call that simply X meters. Forgive me, the diagram is not so accurate. So distance from point A to the point of section, we call it X meters. So which means it actually started from point A to the point of section. So what now is this distance at point A? So we have to take boundary conditions, and the boundary condition is simply what? At point A, okay, X is actually what? 0, because at point A, X doesn't have a value. X there becomes 0. Also, the value of Y is called deflection. Y stands for deflection. I've said the Y, the X here is a slope equation. Meanwhile, Y here is called the deflection equation. So at point A, there is no distance, so X is equal to 0. Also, deflection at that point, Y is equal to 0. So all we need to do is simply what? Substitute these values into what? This equation. If I put in the value of Y as 0 here, automatically everything here becomes 0, because I will simply have EI multiplying 0. Everything there becomes 0. If I put in X here as 0, I will have RAX over 6. RA over 6 multiplies 0. So everything here becomes 0. C1X, X is 0. So everything here becomes 0. Same thing happens here. I will simply have 0 minus 2. Okay, let me just do it. Applying boundary condition. Okay, simply BC stands for boundary condition. We have two conditions to apply here. The first boundary condition is where at point A. That's the first boundary condition. And the final boundary condition is when X finally runs down towards point D. Okay, so at point A, X itself is equal to what? 0, because at this point, X doesn't have any distance. So X is directly what? 0. And at this point, this deflection, Y here stands for deflection. Deflection Y is what? Completely 0 at that same point. So Y is also 0. So if we have this, we can now substitute these two values into what? This equation. That helps us to find the constants. So if we do that, we said Y is 0 at point A, X is also 0. So from here we have EIY. Okay, we have EIY. So that simply means EI, okay, Y is now what? 0. And that's equal to, we have here RA over 6, all multiplying by X. X is 0, okay, plus C1X, X is also 0, plus C2, okay, Macaulay's bracket, we have minus W1 all over 6, okay, into X here is 0 minus 2 all cube into minus W2 into X is 0 minus 3 minus 4 all cube all over 6. So we have this. Take note, EI multiplies 0 simply gives us here as 0, and that's equal to Same thing here, R8 over 6 multiplied 0 gives me here 0 plus C1 multiplied 0 also gives me 0 plus I'm left with C2. But observe the Macaulay's bracket now. I have minus W1 into, of course, here becomes 0. So I'm left with what? Minus 2 all cube. Okay. Okay. Next is simply minus W2. This is over 6. Okay, into this is minus 4 all cube. This is also over 6. Now here is the rule. From Macaulay's method, every value inside the Macaulay's bracket that is less than 1 automatically becomes 0. In the Macaulay's bracket, every value that is less than 1 automatically becomes 0. And if you look at the Macaulay's bracket, I have minus 2 inside this bracket. And of course, minus 2 is less than 1. So this will be considered automatically as 0. Same thing here, I have minus 4 here. And minus 4 is less than 1. So that means this will be automatically considered as 0. So so this actually means that 0 is actually 0 plus 0 plus C2 plus 0 plus 0. Of course, in the Macaulay bracket, every variable or every number less than 1 should be taken completely as what? 0. So these two are completely 0. So this actually implies that C2 is equal to 0. Okay, so if C2 is equal to 0, you plug it back into this deflection equation. You're simply going to have EI y is now equal to, so we have RA x all over 6, okay, plus C1x. Of course, C2 is off, is 0, so that one is off. Put down your Macaulay's bracket, minus W1 into x minus 2 to the power of 3 all over 6, okay, minus W2 into x minus 3 minus 4 to the power of 3 all over 6. So I have this. So that satisfies the first boundary what? Condition. So we now take the final boundary condition is simply what? At point D. So from when x finally runs from point A down to point D, what is now what? The value of x. Now at D, observe that x becomes the total length from point A down to point D. And from here is simply 2 plus 2 plus 2, which is actually what? 6 meters. So our dx is actually equal to 6. And there is no deflection at point D. Take note, point D here, there is no deflection about this point. Since there is no deflection about this point, it means y is equal to 0. Just like we said, at point A, there is no deflection. So deflection at point A becomes 0. Same thing happens here at point D, y becomes 0. So we simply substitute these values into where the equation to find the first constant. And if we do that, we are simply going to have this becomes EI. In place of y here, I will simply call it 0. And that's simply equal to, here is RA. X here is simply what? 6. So times 6 all over 6. Okay. Plus, we have here C1. In place of x here is 6. So simply 6 C1. You put down your Macaulay's bracket minus W1 into x here is 6, so that becomes 6 minus 2 to the power of 3 all over 6. Okay, put down your Macaulay's bracket minus W2, okay, into x here is 6, becomes 6 minus 4 all over 3, sorry, up to the power of 3 all over 6. So I have this. Okay, so of course, EI times 0 here becomes 0, and this is now equal to, of course, 6 can cancel 6 here. I will simply have R A, okay, plus this is 6C1 from here. Okay, so at this point there is no need to put the Macaulay bracket, you can free it. Minus 6 minus 2 here is 4. So minus W1 into 4 to the power of 3 all over 6 minus W2 into 6 minus 4 here is 2 to the power of 3 all over 6. All right, guys. I think I'll pause the video here. Of course, this reaction does not actually have a value. W1 does not have a value. So to actually obtain a real value for C1 will be a little bit tedious. It's not like it's tedious because we're going to have the values in terms of RA, W1 and W2. So let's just pause the video here. But in general, that is the idea behind Macaulay's method of beam deflection. So what will happen is this: in the next videos, I'll start doing calculations on how to employ the Macaulay's method to carry out deflection of beams. All right, guys, thanks very much. I hope you find this video very interesting. Please, if you do, don't forget to share your thoughts in the comment section. I will see you in the next video. Thanks and cheers.